Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to your YouTube channel Chandan Physics. In this video, we are going to discuss growth and decay of current in RC and LR circuit. Let's begin. First, we consider RC circuit. Let a resistor R and a capacitor C be joined in series to an electrochemical cell. That electrochemical cell having an EMF E through a key K. Capacitor having capacitance C, resistor having resistance R, connected to an electrochemical cell having potential E, electrochemical cell having EMF E, that is connected with the key K. First case, charging of a capacitor. Charging of a capacitor means when that key is inserted, a transient current begins to grow in the circuit which charges the capacitor. A potential difference, that is potential V of C, potential across the capacitor is set off, and that V of C is equal to the potential across the capacitor V of C is equal to, let Q is the charge at that instant divided by, let C be the capacity of that capacitance. So, potential developed at that time throughout that of capacitor is V of C is equal to Q by C. Similarly, the potential difference V of R is set off across the resistor, which is equal to V of R is equal to I into R. I is the current, R is the resistance offered by that of resistor. Now, the EMF E of the source E is equal to, therefore, the EMF E is equal to Vc, potential drop across capacitor, plus potential drop across resistor V of R, or E is equal to Vc, that is Q by C plus IR, that equation number 1. Now, we take the condition when at time t is equal to 0, t is equal to 0 means when that key is closed. What happened at that particular case? The charge Q on the capacitor is 0 and so the initial current I naught, that is the maximum, that is maximum current in the circuit, and is given by I naught is equal to E by R. Okay. Again, at the same situation, at this time t is equal to 0, that is t is equal to 0, what happened? The potential drop is entirely across the resistor. When the capacitor is charged to maximum value, that is Q. At that case, the current in the circuit becomes 0. And the potential drop is entirely across the capacitor. Now, here putting I is equal to 0, putting current I is equal to 0 in equation 1. So, E is equal to Q by C. We have the maximum charge, maximum value of charge Q, that is E is equal to Q by C, or Q is equal to C into E. Here I put I is equal to 0, so that equation changes to Q is equal to C E. Since the EMF in that of equation 1 is constant, since EMF, that is E, in equation 1 is constant, therefore differentiating equation 1 with respect to time, we get this d E by dt is equal to d by dt of q by c plus d by dt of IR, or d by dt is the constant, therefore the term will be 0, 1 by c to that of outside, so dq by dt plus r di by dt, or 0 is equal to dq by dt, that is I, so I by c plus r di by dt, or di can be written as di when these terms are to that side, so minus I by RC dt, the equation number 2. Now we use the condition, since resistance R and capacitance C are constant, we integrate equation number 2 using the initial condition that at t is equal to 0, so the current be the maximum, I is equal to I naught, therefore integrating that equation number 2, so di divided by I to this side, integrating from maximum current to its minimum I naught to I is equal to minus 1 by RC integration from dt, time from 0 to maximum, 0 to t, or that is log I base e using the limit I naught to I is equal to minus 1 divided by RC t from 0 to maximum t, or upper limit minus lower limit, so log I base e minus log I naught base e is equal to minus, so that value be the t, so t divided by RC, log a minus log b, that is log a by b, so log I divided by I naught base e is equal to minus t divided by RC. Or taking the antilog, I divided by I naught is equal to e to the power minus t divided by RC, or I is equal to I naught times e to the power minus t by RC. That is the expression for current at time t. The quantity RC is treated as tau, which is known as time constant, that is known as time constant of RC circuit. When t is equal to RC, let we put when T is equal to RC, then the expression for transient current, the expression for transient current becomes I is equal to I naught e to the power minus 1, or I is equal to I naught divided by the value of 1 by E, that is 2.718. Calculating that term, it will be 0.367 I naught. So we can define the time constant tau. Hence, the time constant tau of a RC circuit is defined as the time taken by the capacitor to decrease the current to 0.367 times to its initial value, that is I naught. In this way we define the time constant tau of a RC circuit. If we plot a graph between time and current, time t in x direction, current I in y direction, that point be the maximum current I naught. So the graph is looking like this, and I is equal to I naught e to the power minus t by RC. This is the scenario when charging of a capacitor. Next scenario, discharging of a capacitor. This is the growth of current, then the decay of current. Next scenario, discharging of a capacitor. Discharging of a capacitor in case of RC circuit. Look here, when that key is open, what happen? There is a potential drop or potential difference of capital Q by C across the capacitor, since it achieves the maximum charge. So potential drop in that of capacitor be capital Q by C, and zero potential difference across the resistor, since there will be no current, means I is equal to 0 at that case when that key is open. Now the capacitor starts discharging. Now we can use the Kirchhoff's second law. In that of mesh, what we have? By using Kirchhoff's second law, the potential drop here, the EMF is equal to 0, that is Vc plus VR. here EMF is equal to 0 is equal to Vc plus VR. So 0 is equal to potential drop across that capacitor Q by C plus resistor 1 by R or minus IR is equal to Q by C or minus R in place of I, that is dq by dt is equal to Q by C or dq by Q is equal to minus 1 by RC into dt. Now integrating the above equation, using the condition that is Q is equal to maximum charge at t is equal to 0 in case of discharging of that of capacitor. So we have dq by Q from maximum charge to its minimum value minus 1 by RC integrating time from 0 to t or log Q by capital Q base E is equal to minus 1 by RC into t, or taking the anti-log, and here that is log Q using upper limit and lower limit, and solving it we have logarithmic term. So taking anti-log, and finally the result of Q is equal to Q times e to the power minus t by RC. We know that I is equal to dq by dt. We know I is equal to dq by dt. Therefore, d by dt of Q, that term, that is Q e to the power minus t by RC, or I is equal to, that is Q by RC e to the power minus t by RC. So I Q by RC, Q be the maximum charge, to that of RC be the time constant. So charge for time, that be the maximum current I naught e to the power minus t by RC. Hence, by taking the first case, here I is equal to I naught e to the power minus t by RC. Here I is equal to I naught e to the power minus t by RC. So what we conclude here? So the conclusion be, we conclude that both during charging and discharging, as well as discharging, the capacitor through resistor the current decreases exponential at a rate characterized by the time constant tau is equal to RC. Okay, that is the conclusion from both these two cases. Here we discuss growth and decay of current in case of RC circuit. When the capacitor is charged, we have that expression and defining the time constant of RC circuit, and when capacitor is discharging of capacitor condition, we have the expression for current. From these two points as charging and discharging, we conclude that one. Next, in case of LR circuit, let an inductance L and resistor R be connected in series with an electrochemical cell having EMF E. Having EMF E here. First case, growth of current. Growth of current. When that key is closed, the growth of current from 0 to maximum value let I naught takes place. During this time, an induced EMF is produced across the inductor having inductance capital L. This induced EMF opposes the growth of current by using the Lenz's law. Now, the induced EMF across that inductance be V of L, and that V of L is given as minus L di by dt, where I is the current at any instant during the growth and di by dt is the rate of growth of current, and L is the coefficient of self inductance, or we can say self inductance of the coil. Now, the potential drop V R across the resistor having resistance R. So, V R is equal to I into R. We can use Kirchhoff's second law with the proper sign convention. So, what we have, using KVL, we have E is equal to the EMF VR minus VL, VR minus VL. This is because the current I increases, di by dt becomes positive, therefore, VL is negative according to Lenz's law. Now, the values are putted here. We have E is equal to minus IR minus of minus L di by dt, minus minus plus. So, E is equal to IR plus L di by dt. when the current attains the maximum value I naught, when current attains maximum value I naught, then the induced EMF, that is V of L is equal to 0. Then that equation is equal to that term L di by dt is equal to 0, that is L di by dt is equal to 0. Instead of L di by dt you can put 0 and I replaces as I naught is equal to I naught into R. Let equation number I, that be equation number I. Comparing 1 and 2, comparing I and I, we get I naught R is equal to IR plus L di by dt, that to this side. So, taking R as common, so I naught minus I is equal to L di by dt, or di divided by I naught into I naught minus I is equal to R by L dt. Now, integrating both sides, integrating both sides, we get integration over di divided by I naught minus I is equal to R by L integration over dt. Let here we can use the condition as 0 to t. That be the log I naught minus I of base E divided by minus 1 plus C with the integrating constant is equal to R by L, the value of t from 0 to t, where C with the integrating constant, where C is the integrating constant, or log I naught minus I base E plus C, minus is multiplied here, so minus R by L into t. Now, the constant of integration can be evaluated by taking the condition when t is equal to 0, I is equal to 0, then integrating constant C will be minus log I naught base E. By putting this boundary condition, C is evaluated, therefore log I naught minus I base E minus log I naught base E is equal to minus R by L into t, or log A minus log B. So, log A by B I divided by I naught base E equal to minus R by L into t. Taking the anti-log, we have I naught minus I divided by I naught is equal to that term. So, finally, I naught I divided by I naught is equal to e to the power minus r by l into t, or I naught is multiplied here. So I naught as taking common, that is I naught minus I is equal to I naught times e to the power minus r by l into t, or finally I is equal to I naught taking as common I naught times 1 minus e to the power minus r by l t. And with the expression, now that equation is the Helmholtz equation. This is the Helmholtz equation for growth of current in LR circuit. Helmholtz equation for growth of current in LR circuit. Now L by R has the same dimension of time. Therefore, since L by R has the same dimension of time, so the term L by R is called time constant of LR circuit. When use the condition time is equal to L by R, then putting t is equal to L by R, so I is equal to I naught times 1 minus e to the power minus 1, I naught 1 minus 1 by 2.718, and solving I naught 1 minus 0.368, and the value of I is equal to 0.632 times of I naught. So here we define the time constant. Thus time constant is defined as time constant in LR circuit is defined as the time during which the current grows from 0 to 0.632 times the maximum value. Time constant in LR circuit defined as the time during which the current grows from 0 to this times of the maximum value. This is the first case, that is the growth of current in LR circuit. Now decay of current in LR circuit. Second one, decay of current. Look here, when the current in that of circuit is switched off, at that of case an induced EMF is produced in the inductance which slows down the rate of decay of currents. Since there is no source of EMF in that of circuit, at that of case E is equal to 0. So, the induced EMF in that of inductance, that is minus L di by dt, produces a potential drop across that resistor which is equal to I into R across that of resistor. So, the current starts decaying from maximum value to 0. So, we can use the KVL here. So, using KVL in that of circuit, using Kirchhoff's voltage law, E is equal to VR plus VL. Here E is equal to 0, VR is equal to IR plus VL is equal to L di by dt, or minus L di by dt is equal to IR, or di by dt is equal to minus R by L dt. Now, integrating we obtain, we get log I base E is equal to minus R by L t plus C, where C is the integrating constant. C is the integrating constant. Now, that value of integrating constant can be evaluated by putting the condition when t is equal to 0, then I is equal to I naught, and C, that integrating constant, will be log I naught base E. Now, put the value of C here, log I base E is equal to minus R by L t plus log I naught base E, or log I base E minus log I naught base E is equal to minus R by L into t, log A minus log B, that is log A by B, log I by I naught base E minus R by L into t, or taking the antilog, that is I by I naught is equal to e to the power minus R by L into t, or I is equal to I naught times e to the power minus R by L into t, which is, this is the Helmholtz equation for decay of the current in LR circuit. Now, if we plot the graph between the time and current, let we plot the graph between time, next direction, and current in y direction, that be the maximum value of current I naught. So, in case of growth, I is equal to I naught 1 minus e to the power minus R by L into t. So, that growth case, the exponential curve looking like this. And in case of decay, I is equal to I naught e to the minus R by L into t, the exponential curve is looking like this. This is the graphical representation of growth and decay of current in case of LR circuit. In case of LR circuit, growth of current, Helmholtz equation of growth of current in LR circuit, defining the time constant of LR circuit. Then decay of current in LR circuit. Here we use KVL as E is equal to 0. For that condition, when key is switched off, this is the expression for current. This is the Helmholtz equation, decay of current in LR circuit. Graphical view of growth and decay of current in LR circuit. So, with the help of this video lecture, we understand the concept of growth and decay of current in LR and RC circuit. So, in case of RC circuit, charging of capacitor, discharging of a capacitor, again for LR circuit, growth of current, and decay of current. So, with the help of this video lecture, we understand the growth and decay of current in case of LR and RC circuit. So, with this useful and informative notes, let me wind up this session. Thank you.